Welcome to the deep dive. Today we're plunging into something truly dynamic, the constant motion of the ocean. You've gathered some great sources for us on how all that water actually moves.
That's right. It's easy to think of the ocean as just
Yeah,
there, but it's always moving. The material we have really helps unpack the why behind it all.
exactly. So our mission really is to get a handle on these movements. The waves crashing, the tides coming in and out, these huge currents flowing underneath. How does it all work? And importantly, why should we care?
Well, and the sources point to this constant interplay, right? You've got the water's own characteristics, temperature, saltiness, density, and then these big external forces.
Like the sun and moon.
Yeah, the sun, the moon, and definitely the wind, all interacting.
Okay, let's start with the most obvious one, maybe. Waves. When I picture the ocean moving, that's the first thing. But what are they, fundamentally? It looks like water rushing in.
Right, and that's a really common perception. But the key insight from the material is that waves are mostly about energy moving across the surface, not the water itself traveling huge distances.
Ah, okay. So the water molecules aren't actually surfing across the ocean.
Exactly. Think of it more like, well, like doing the wave in a stadium. People stand up and sit down, the wave moves, but the people mostly stay put. Water particles move in a circle as the energy passes.
Okay, a circular motion. But they end up pretty much back where they started.
Pretty much, yeah. The shape of the wave moves forward, the energy moves forward, but the water itself doesn't travel far with it.
That makes more sense. So where's this energy coming from?
The vast majority comes from the wind. Simple friction, really. Wind blows on the water, drags it a bit, transfers energy, and starts those ripples.
And those ripples can grow into massive waves.
They can, yeah. How big they get depends on three main things the wind does.
Okay.
How fast it's blowing, how long it blows continuously, and the distance over the water it blows across. That distance has a name.
Fetch. Fetch. Right. So a hurricane blowing for days over the open Atlantic, that's going to build some monsters.
Precisely. Compared to, say, a quick breeze across a lake. The sources also mention that choppy, steep waves you see near shore, they're often young from local winds, but those big, smooth, rolling waves, the swell that can arrive on a calm day, that energy might have traveled from a storm thousands of miles away.
Wow, energy traveling that far. So how does the wind pushing actually create that up and down wave shape we see?
It's this constant interplay between the wind's push and gravity. Wind starts a disturbance, makes a crest. Gravity pulls that crest down.
Trying to flatten it out again?
Exactly, but pulling the crest down pushes water up nearby, forming a trough. Then gravity pulls that down, pushing up the next crest, and the wind keeps adding energy, so the waveform moves forward.
So it's like gravity keeps trying to restore calm, but the energy won't let it.
That's a good way to think about it. And the sources give us the terms. Crest is the high point, trough is the low point, wave height is the distance between them vertically.
An amplitude, that's half the height.
Correct, from the middle level to the crest or trough. Then you have the wave period. That's the time it takes for one full wave cycle, like crest, to pass a point.
And wavelength is the distance between those crests.
Right, the horizontal distance. And wave speed, sometimes called drift in the context of general movement, is how fast that wave pattern travels, usually in knots. Frequency is just how many waves pass by per second.
Okay, got the basics. What happens when these waves, carrying all that energy, finally reach the shore? They change dramatically.
They really do. As the water gets shallower, the bottom part of that circular water motion starts to drag on the seabed. Friction.
So it slows down.
The bottom slows down, yes. But the energy is still piling in from behind. So the wave starts to bunch up. The wavelength gets shorter, but the height increases. It gets taller.
That's when you see it rear up before crashing.
Exactly. It becomes steeper and unstable. And when the water depth gets too shallow, roughly less than half the wavelength, the material says the top part, the crest, outruns the base. It becomes too steep to support itself, and it just collapses.
It breaks, releasing all that energy.
Yep, that's the surf. And it's important to remember, as the sources point out, this wave action is mostly a surface thing. It really doesn't disturb the deep ocean bottom much at all.
Okay, so that's waves, wind energy moving across the surface. Let's shift gears. There's another huge ocean movement, but it feels different, more regular, more vertical. Tides.
Right. Tides are that predictable rise and fall of sea level. Totally different mechanism than waves. It's not about wind. It's not about storms causing surges, though those happen too. Tides are, well, astronomical.
Astronomical. So outer space.
Pretty much. The main driver is the gravitational pull of the moon. And, to a lesser extent, the sun also plays a role.
Okay, Moon's gravity pulls the water. That makes sense for the high tide on the side of Earth facing the moon. But why is there another high tide on the opposite side at roughly the same time? That bit always confused me.
Yeah, that's a classic point of confusion. It's not just the direct pull. You have to think about the Earth and Moon orbiting a common center of mass, and inertia plays a part. The Moon's gravity pulls strongest on the water nearest to it, creating that bulge. But the Earth itself is also being pulled towards the Moon. The water on the far side experiences less gravitational pull than the Earth's center does. So relative to the Earth, it gets sort of left behind, creating another bulge there due to inertia. The key is the difference in gravitational pull across the Earth. That's the tide-generating force.
Okay, so two bulges, one pulled towards the moon, one sort of lagging behind on the far side.
Exactly. And as the Earth spins on its axis, different locations pass through these bulges. When you're in a bulge, it's high tide. When you're between them, low tide.
And since the Earth spins once a day and the moon moves a bit, that's why we get roughly 2 high tides and 2 low tides a day in most places.
Precisely. Roughly every 24 hours and 50 minutes, you pass through 2 highs and 2 lows.
Does the shape of the land matter here like it does for waves?
Oh, hugely.
Yeah.
Maybe even more for the height of the tide.
Yeah.
The moon and sun create the potential, but the actual range, how high the high tide gets and how low the low tide gets, depends massively on the shape of the coastline and the ocean basin.
How so?
Well, the sources mentioned tides are amplified on wide, shallow continental shelves. They're much smaller out in the deep ocean around islands. And if you have a coastline shaped like a funnel, like a bay or estuary that narrows,
It channels the water.
exactly. It forces all that incoming tidal water into a smaller space, piling it up. That's where you get really extreme tidal ranges.
Like the Bay of Fundy.
The classic example, yeah. In Canada, its shape is perfect for amplifying the tide, leading to the world's highest, we're talking 15, sometimes 16 meters difference between high and low tide. That funneling also creates really strong tidal currents.
Wow, 16 meters. Okay, so geography shapes the height. The sources also mention different types of tides based on frequency.
That's right. Most common is semi-diurnal, 2 high tides and 2 low tides each day, and they're roughly the same height.
Okay.
Then there's diurnal, just 1 high and 1 low per day. Less common.
And then mixed?
Mixed tides are where the heights vary. You might get 2 high tides, but one is much higher than the other. Or the low tides differ, common on the U.S. West Coast, Pacific Islands, that sort of area.
And then there's spring and neap tides. That's about the sun and moon lining up, right?
Exactly. This affects the range of the tide over a month. When the sun, earth, and moon are all in a line during a new moon or a full moon, their gravitational pulls add up.
Stronger pull.
Stronger combined pull, yes, which means you get higher high tides and lower low tides. The overall range is bigger. Those are spring tides. Think springing high.
Got it. And neap tides.
Neap tides happen about a week later when the sun and moon are at right angles to each other relative to Earth, like during the first and third quarter moons.
So their poles kind of work against each other.
Partially, yeah. The sun's gravity counteracts the moon's pull to some extent. The moon still dominates, but the result is lower high tides and higher low tides. The overall range is smaller. Neap tides are the weaker ones.
And the sources even mention the orbits aren't perfect circles.
Right, little extra factors. When the moon is closest to Earth in its orbit, that's called perigee, its pull is stronger, so tides are a bit higher than average. When it's farthest away, apogee tides are a bit lower.
Same for the Earth and sun.
Yep. Earth is closest to the sun perihelion around early January. That gives the sun slightly more influence, boosting tides a tiny bit globally. Farthest away aphelion around early July, slightly less influence.
So many layers. And the terms for water moving in and out.
When the water level is falling, moving away from shore, that's the ebb tide. When it's rising, coming in, that's the flow or flood tide.
Okay, so beyond just being predictable, why are tides so important?
Oh, hugely important. Practically, their predictability is vital for shipping. Knowing when the water is deep enough to get into shallow ports, for instance. Fishermen depend on tide charts, too. Ecologically, they flush out estuaries, keep the water circulating, prevent silt buildup. And increasingly, we're looking at harnessing that incredible power. Tidal energy.
Right, renewable energy. The sources mentioned projects.
Yeah, places like Canada, France, Russia, China are using it.
Yeah.
There was mention of potential in the Sundarbans in India, too. It's a massive, predictable power source if we can tap it effectively.
Okay, fascinating. So we've had wind-driven waves, cosmic tides. What's the third big piece? Currents. The sources describe them like rivers in the ocean.
That's a great analogy. Ocean currents are these continuous directed movements of seawater, flowing along specific paths, sometimes for thousands of miles. True rivers within the ocean.
What gets these giant rivers flowing? It can't just be wind, can it? Not for the whole ocean depth.
It's a combination. The sources break it down nicely. You have primary forces that start the water moving. Things like, well, solar heating near the equator makes water expand slightly, creating a tiny slope.
Okay.
Wind dragging the surface, obviously a big one for surface currents. Gravity pulling water down slopes. And crucially, the Coriolis force.
Ah, Coriolis again. Same as with wind, deflecting things because the Earth spins.
Exactly the same principle. It deflects moving water to the right in the northern hemisphere and to the left in the southern hemisphere. This is key to organizing currents into those huge circular patterns you see on maps, the gyres.
Okay, so those forces start moving and Coriolis shapes the path. What about other influences? Secondary forces.
This is where density comes in big time. Remember, denser water sinks. Less dense water rises or floats. And density depends mainly on temperature and salinity.
Colder is denser, saltier is denser.
Correct. So cold, salty water is very dense. It forms in polar regions, sinks deep, and then flows along the ocean floor towards the equator. Meanwhile, warmer surface water flows from the equator towards the poles to replace it. This density difference drives the deep ocean circulation, sometimes called the global conveyor belt.
So wind drives the surface stuff, maybe the top few hundred meters, and density drives the deep stuff.
Largely, yes. The material classifies them. Surface currents, maybe the top 10% of the ocean volume, down to about 400 meters, mostly wind-driven. Deep water currents make up the other 90%, driven by these density differences, sinking mainly at high latitudes. The sources also mention things like the thermocline, a sharp change in temperature with depth, and halocline, sharp change in salinity, which mark these density boundaries.
And like waves and tides, they're classified by temperature this time.
Yep. Cold currents bring cold water towards warmer regions. Warm currents bring warm water towards colder regions. Their locations are pretty typical. Cold currents often run along west coasts and lower latitudes, warm currents along east coasts. It flips a bit in higher latitudes. There are always complexities, but that's the general pattern.
And how fast are these ocean rivers?
Their speed, again called drift, varies a lot. Surface currents, like the Gulf Stream, can be really fast, several knots. Deep currents are much, much slower. Think less than a knot, maybe centimeters per second. But they move immense volumes of water over long timescales.
And you mentioned wind linking to surface currents. Are ocean currents linked to atmospheric patterns overall?
Absolutely. Prevailing winds are a primary driver for surface currents, so the major ocean gyres tend to mirror the major atmospheric pressure systems and wind patterns. The ocean and atmosphere are deeply coupled systems.
So these currents are moving massive amounts of water. What's the big impact of that?
It's fundamental to our planet's climate system. Currents transport incredible amounts of heat. Just like the atmosphere moves heat around, the oceans do too. Warm water flows from the tropics poleward. Cold water flows from the poles toward the equator. It's a global heat distribution network.
And that directly affects the weather on land.
Hugely. The sources give great examples. Look at west coasts in the subtropics next to cold currents, often very dry, like deserts. Think Peru or Namibia.
Right.
Now contrast that with west coasts and higher latitudes next to warm currents. Western Europe, heated by the North Atlantic Current, or the Pacific Northwest. Much milder and wetter climates than you'd expect for their latitude. East coasts often get warm currents too, influencing their climates.
And what about life in the ocean? Fishing.
Ah, yes, critical connection. Where different currents meet, especially warm and cold ones, you often get mixing. This mixing can bring nutrient-rich deep water up to the surface, a process called upwelling. Those nutrients, plus sunlight-fuel explosive growth of phytoplankton, the base of the entire marine food chain. So these mixing zones where currents converge are incredibly rich fishing grounds. Some of the best in the world are found where currents meet.
Wow. So we've covered the energetic dance of waves, the rhythmic pull of tides, and these vast, slow-moving current rivers, from surface to deep, driven by wind, gravity, the moon, the sun, density.
It really paints a picture of a constantly churning, interconnected system, doesn't it?
Yeah.
Each type of movement playing its part.
Absolutely. And understanding it isn't just, academic. It touches everything. Climate, where fish are, how ships navigate, even potential future energy sources. It's fundamental.
Which leads to a final thought, maybe something for you to ponder. Given how interconnected this whole system is, waves, tides, currents, heat transport, what happens if you change one part? Well, imagine a significant change in water temperature, or maybe salinity, in one key area, perhaps due to climate change. How might that small initial change ripple through? Could it alter a major current path, change where heat gets distributed, affect those vital mixing zones for fisheries, or even influence weather patterns thousands of miles away? How far could the effects of one local change actually reach in this vast, connected ocean?
That's a powerful thought. The interconnectedness, the potential for distant impacts. A lot to think about in the dynamic ocean. Thanks for this deep dive. And keep noticing those powerful forces at work next time you see the ocean.